Let A and B be irrational numbers. Can A to the power B be a rational number? The answer is yes. I'm going to present three approaches. The first one is famous, a very clever solution. I will also present another couple of approaches based on countable sets and transcendental numbers. Both methods need some background of real analysis and method theory. The first solution, consider square root of 2 to the power of square root of 2. Is this rational? Not likely, but we really don't know. There are two cases. One, it is rational. In this case, let A equal B equals square root of 2. Then they are both irrational, and A to the power B is rational based on the assumption. Case 2, it is not rational. In this case, we define A is this irrational number, and B is simply square root of 2, also irrational. We calculate A to the power B, plug in the numbers, simplify them. We got 2, which is rational. Irrational to the power of irrational is irrational. We are done again. We really don't know if square root of 2 to the power of square root of 2 is rational. But it doesn't matter. In either case, we find an example. The second method, we start with a definition. A set of real numbers is called countable if there exists a one-to-one and onto mapping between the set and the set of all natural numbers. Countable set is a concept in measure theory. As an example, the set of all rational numbers is countable. In other words, we can establish a one-to-one and onto mapping between all rational numbers and all natural numbers. However, it is impossible to establish such a mapping for irrational numbers. So we call the set of all irrational numbers is uncountable. As a matter of fact, the real numbers are almost all irrational. You know what I'm talking about if you learned measure theory or real analysis. Let S be a set consisting for all numbers of form 2 to the power of 1 over R, which are irrational. Because the set of all irrational numbers is uncountable, S must be uncountable as well. On the other hand, all rational numbers form a countable set. There are too much more elements in S. There must be some irrational numbers in it. Assume 2 to the power of 1 over t be an irrational number in S. T is an irrational number. We let A to be the number 2 to the power of 1 over t, irrational, and B is t, also irrational. We calculate A to the power B. Plug in, simplify, we got 2, which is rational. For the third method, we have another couple of definitions. A number is called algebraic if it is a root of a non-zero polynomial with integer coefficients. A number is said to be transcendental if it is not algebraic. Here are some examples of algebraic numbers. First, x is 2/3. It is the root of linear polynomial 2x minus 3. You can see that all rational numbers are algebraic. Some irrational numbers can also be algebraic. For example, x is square root of 2. It is a root of x squared minus 2 equals 0. You see, it is a quadratic polynomial with integer coefficient. A more complex example, x is square root of 2 plus cubic root of 3. It is actually a root of a 6th order polynomial with integer coefficient. You can check it. Question: are there any numbers that are transcendental, mean not algebraic? The answer is yes. Actually, the two famous irrational numbers, pi and e, are both transcendental. This is based on Lindemann-Weierstrass theorem. As a matter of fact, almost all real numbers are transcendental. We know e to the power natural log of 2 equals 2, and e is irrational. We are done if we can prove that log of 2 is irrational. Assume not, it is a rational number. Then log of 2 can be expressed as a fraction of m over n with integers m and n. By the definition of logarithm, we have e to the power m over n equals 2. Raised to the power n, we have e to the power m equals 2 to the power n. What does that mean? It means that e is a root of polynomial equation with integer coefficient x to the power m minus 2 to the power n equals 0. This is impossible because e is a transcendental number. Thank you for watching. Please consider subscribe my channel. I appreciate your support.